All right, so I've gotten an hour and a half to go through 50 pages of notes. No, I'm not going to do that. So you must have gotten an email with a PDF document, which is quite long. I'm not going to go through all of it, and that's the whole point of giving you the document. The idea is that there's a wide range of backgrounds here. Some of you deserve some introductory material, very introductory material. Some of you deserve something a bit more advanced. And to appease all of you, I sweated a bunch of ink onto these pages. So one advantage here is that a lot of the details of the things that I'm going to talk about, like derivations of certain things, I'm not going to do. There are a lot of blackboards, but there are not that many blackboards. So you can use these notes as a reference. I'll point to them as we go through the lecture. For example, I'm not going to derive the MHD equations on the board. I'm just going to put them down by fiat, and we can discuss things physically. And if you have questions, please feel free to interrupt. And let's get started. So just following on the disclaimer that I put on the second page of the notes that you have, I mean, what I'm going to present is by necessity incomplete, right? I mean, you can't do MHD in an hour and a half. The idea here is to provide you with some MHD that has an astrophysical context. It's the style of MHD that astrophysicists practice. There will be two talks focused more on magnetic confinement fusion, and I do highlight a few things in the notes that point towards very strongly magnetized plasmas like terrestrial plasmas. I'm not going to talk about them in the lecture because there's just not enough time, and you'll get enough of that from Michael Barnes later in the week. But I think it's important, despite the notes being, I think, extensive, there's a lot missing here, and I encourage you to go out and use this as a springboard to dig up some textbooks and go exploring. Right, so this is an introduction to plasma physics to give you some background for the rest of the week. So the first thing that you have to consider is, what is a plasma? What do we mean when we talk about a plasma? And that's actually an extremely difficult question to answer. The reason plasma physics is so popular, people want to say that they work on plasma physics even when it might not quite be true. For example, warm dense matter is often classified under plasma physics, even though it doesn't share a lot of properties as other plasmas. Protoplanetary disks that you might learn about later in the week are extremely poorly ionized, and yet we refer to them as plasmas in the MHD context. So one thing that I wanted to do was just, this diagram's already in the notes, but I put it on the board before you came in to show you the diversity of plasmas when somebody talks about what is plasma physics. So it's quite difficult to classify all these things under one umbrella. So here we've got a range of 8 orders of magnitude in temperature, which, by the way, with apologies to Boltzmann, the constant's gone. So all the temperatures are just T, and they're in energy units. And this is 35 orders of magnitude in density. And these are plasmas. The interstellar medium sort of straddles the line between an ionized plasma and a poorly ionized plasma. It's got a lot of neutrals. Here's the solar wind. If you go to galactic center, the Sagittarius star lives about here in this space. The intracluster medium of galaxy clusters, Elliot's going to talk about this later. The solar corona, light bulbs. Current experiments in fusion, and if you were able to do nuclear fusion, this is where a reactor would live. Here's the center of the sun. Here's laser fusion experiments. All the way up here is relativistic. I put this here to let you know that I'm doing nothing near this line. So I'll pretty much stay in the non-relativistic regime. And down here are metals. Here's some white dwarfs. And this line is pretty much the only solid definition of what constitutes a plasma. You might look up in a textbook what's a plasma. It'll say a sufficiently ionized gas, defined sufficiently. Protoplanetary disks have degrees of ionization of 10 to the minus 10, 10 to the minus 11, 10 to the minus 12, and yet these are still MHD systems. They're non-ideal MHD systems, but they're still MHD systems. So you have to be very careful what you mean by this kind of definition. But one thing that's quite solid, with apologies to warm dense matter people, is this line, which is the plasma parameter. It's the number of electrons in a Debye sphere. And this underlies the concept of what's called collective behavior. So I'll write this on the board. Here's the chalk. So the definition's right here. So it's the number density of your plasma times the cube of the Debye length. So you probably learned the Debye length at some time. Essentially, it's where electrostatic, like Coulomb interactions, are screened. So if you were to write down electrostatic potential in a system of mobile charges, it'll have the usual 1 over r, but then it'll have an exponential suppression on the Debye length. And that's just because if you have an ion, you also have a cloud of electrons around it that provide just screening of the charge. And the reason why the Debye length is important to the definition of a plasma is that this marks the dividing line between roughly the kinetic energy that's in the random motions of the particles, like the temperature, and the potential energy, which is just from Coulomb interactions on the scale of a Debye cloud. So, kinetic energy is just temperature, and potential energy is some charge divided by lambda Debye. You can also show that this is a statement about the ratio of the mean free path to the Debye length. And all the plasmas that we're interested in have this as a huge number. So the idea is that you don't, if you have a collection of particles, you don't have to go counting pairwise interactions and amongst 10 to the 28 particles. That you can treat this as a collection of particles that are interacting with some smooth background, and the smooth background is achieved because of this electric screening. And you refer to that as a collective plasma, something that demonstrates collective behavior in this way. Good. So plasmas are diverse. They're very hot. They're very cold. They could be partially ionized. But because they're so diverse, it's really hard to lump them into one category. So instead, what I've done is I've provided, both in the notes and on the board, sort of a rogues gallery of exciting plasmas, at least those that are exciting to me. So in the upper left, that's the solar wind, SW. We're sitting at an AU, so these numbers are characteristic of the solar wind at 1 AU. So if you don't know the solar wind, the outer parts of the sun are, the temperature's hot enough that it's gravitationally unbound and just sort of leaks off at 10 to the minus 13 solar masses per year, fills the interplanetary medium, and we put spacecraft out into it, and you can measure these parameters directly. So the temperature is about 10 eV, the number density is about 10 particles per cubic centimeter, and the field is about 100 microgauss. Of course, this varies widely as you get closer to the solar corona, but these are parameters for 1 AU. Other plasmas you might see this week are the intracluster medium. So galaxies come equipped with plasma. And if you go to some characteristic scale in the ICM of 100 kiloparsecs, these are the types of numbers that you expect there. So 8 kiloelectron volts. It's extremely diffuse, so 5 times 10 to the minus 3 particles per cubic centimeter might be a typical number. And lo and behold, just like most of the universe, things are measured in microgauss. The magnetic field there is about a microgauss. I've also given you numbers for the galactic center, which is just GC here. So if you go 0.1 parsecs from the galactic center, which if you're an astronomy student, what I'm about to say will mean something to you. That's roughly the Bondi radius. So it's the gravitational radius. And then I've also given some numbers for the interstellar medium, at least the warm phase. The nice thing about the ISM is everything is just one. You know, it's 1 eV, 1 particle per cubic centimeter. The magnetic field is roughly a microgauss. So that's quite simple. Okay, so these are just numbers. You have to know what these units actually mean. If you come from laboratory plasmas and you're used to Teslas, it might be useful to know that the magnetic field of the Earth is roughly a half Gauss. So you can kind of feel that. So you know, dial that down by 10 to the 6, and that's the magnetic field in the ISM and the intercluster medium. So I've also given a couple other parameters here, which are quite important velocities and length scales and time scales to have at your fingertips when you think about plasmas. One is just the thermal speed. And here, just a warning, you often have to be careful exactly what you mean by this because a lot of people define it without the factor of 2. So just be careful with that. So this is just a measure of the random motions of the particles. For example, if you had a collection of particles that were described by some distribution function that was Maxwellian, that's what I mean by V thermal. It's just the broadness of the random motions. So that should be quite familiar. Where's the hook? So I give some examples of thermal speeds over there on the other board. I think I put them all in kilometers per second. Yeah. So they span about 10 kilometers per second to 1,000 kilometers per second. One thing I didn't write on the board because I didn't have enough room, but it's important for later in the week. It's in the notes, and that's JET, which is the Joint European Torus, which is a fusion experiment. And that's the outlier. You know, if you look at the notes on the charts on page 5 and 6 and 8, you'll see another column. And you'll see that the temperatures are kind of comparable to the hottest systems up there, but the magnetic field is widely different. And the idea there is that, you know, if you want to confine a plasma in astrophysics, you just invoke gravity. That's simple. If you want to confine a plasma on Earth, you have to invoke something else. And so you'll hear later in the week about magnetic confinement fusion, and that's why the magnetic field is so strong in terrestrial plasmas. Right, so there's another speed on the board, which we'll come back to in the lecture, which is the Alfvén speed. I'm using CGS units. It's the only units you should be using. So this is the speed at which a disturbance propagates along a magnetic field. We'll come back to that in the rest of the lecture. The ratio is really important. So a lot of astrophysical plasma physics starts with this parameter, the plasma beta. So one thing that you should note on the board is that astrophysical plasmas and space plasmas are pretty much high beta plasmas, by which I mean anything bigger than 1. So that doesn't mean that the magnetic field doesn't mean that the magnetic field is not important. It just means that the energy content and the random motions of the particles is higher than that in the energy density of the magnetic field. So, you know, if you go to the intracluster medium, we think it's something like 1,000. It might be 100 in some regions, 10 to the 4 in some regions, but just roughly. Now, if you go into the chart and you look at what I wrote for the plasma beta of that joint European torus, it's about 1%. So again, that's the statement I was trying to make of a terrestrial plasma, you need to rely on something other than gravity to confine. And that's why the plasma beta in these systems are so low. Okay, so that's plasma beta. Right, so that's all I have to say about what a plasma is. The next step is defining what a fluid is, because we'll be talking about MHD, which is fluid theory, so one would like to know, when is a plasma a fluid and not a fluid. And this is where the mean free path comes in. So you have pairwise You've got small angle deflections as particles rush past each other and they get scattered. You can characterize this as some collisional mean-free path, which is V thermal times some collision time scale. And I've given some numbers here. And you can tell here that there's a huge variety. So the mean free path in the solar wind is roughly an AU. It's measured on AU. So by the time a particle leaves the solar corona and sweeps past the Earth, it's interacted with another particle statistically once. So this is sort of borderline fluid. But if you look at another system, like the interstellar medium, characteristic scales in the interstellar medium are measured in parsecs or tens of parsecs. And the mean free path is 10 to the minus 7 a parsec. So this is an extremely good fluid in that collisional sense. So what this means is that the distribution function of the particles, which is something I'll talk about in the second lecture, is very close to a Maxwellian. It's nice and isotropic, and that's just enforced by collisions here. Now, if you go to the galactic center and the intracluster medium, you'll notice that the mean free path is actually quite long. And I'll talk about that in the second lecture, what happens to MHD when the mean free path gets long and you start to doubt whether this is really a fluid and can you treat it as a fluid, and under what conditions can you treat it as a fluid, and what kind of equations can you use short of the full Vlasov-Maxwell set. All right, so that's mean free path. What I've given you on page 7, if you want to define a mean free path, you need to know a collision time scale. And because plasmas are widely varied, the collision timescales are very different, whether you're talking about a fully ionized plasma or a plasma where the primary collisions are between charges and a bunch of neutral species, like neutral hydrogen or neutral helium. So I've given you expressions on page 7 that you can serve as a reference to go look up collision timescales between different species and different kinds of plasmas. All right. The last length scale that I'm going to talk about is what I'll denote rho I. So this is, sorry, this is down in the corner. So it's the thermal speed divided by the Larmor frequency, the gyro frequency of an ion. When I say ion here, I really mean proton, but of course you can have a multi-species plasma, like the solar wind has a lot of minor ions with different masses. Here I'm just mean proton. So this is the Larmor scale. This is the size of a gyro orbit of a typical particle in a plasma characterized by some thermal speed. And the thing to really note here is that this is tiny. I didn't even write the numbers for the Joint European Torus down, and it's tiny there too. So in the solar wind, 10 to the minus 7 AU. And the intracluster medium on scales that are the size of the system is like hundreds of kiloparsecs, megaparsec. Rho I is a nanoparsec. In the galactic center, at the Bondi radius, it's 0.2 centimeters. In the interstellar medium, it's 10 to the minus 11 parsecs. So huge scale separations. This is quite characteristic of astrophysical plasmas. So in a lot of these systems, even though the mean free path might be small, like here, it's not smaller than rho I. And what that means is that the particles know about the magnetic field. They're not being deflected by collisions so often that they lose track of the fact that they're living in a magnetized plasma. One of the things that I ran out of board space to give you, but is in page 8 of the notes, is typical gyro frequencies. And for most of the universe, except in relativistic plasmas, they're measured in hertz. So it's quite fascinating, right? It's a gyro frequency that you can measure on human timescales embedded within something that evolves on 10 million years. So just to give you a feeling for the type of scale separation that are involved in astrophysical plasmas. Good, so that's the little introduction survey. Of course, you'll hear a lot more about each of these systems, the stability of the system, the plasma properties of the system. My job is just to make sure that we're all on the same level in terms of the requisite theoretical background. And so for that, I'll just jump right into MHD. So any questions about these numbers yet? Yeah.
What does the subscript I represent? MI and M. What is the difference between MI and M?
Doesn't matter. I mean, we'll come back to this, but technically here, the alphane speed is usually defined in terms of the total mass density of the plasma. But if you have ions and electrons, the mass of the ion is 2,000 times the mass of the electron. And so the mass density is usually dominated by the ions, which are sort of the inertia-bearing species. So that's why this is there. I was just lazy when I didn't put the I's, yeah.
For the definition of plasma,
Yeah.
do you end up using the Larmor radius instead of mean free path over there?
It depends on the plasma. So some things that I'll talk about in the second lecture, yeah, the Larmor radius does play the role of the mean free path in some cases. Well, you know, plasmas are rich. You can find any system where the mean free path is played by something else other than collisions, or sometimes it's just only played by collisions. But yeah, we'll encounter each of these options. Good. So what you could do if you wanted to be proper and rigorous and you have more than an hour and a half to do MHD is that you would write down a kinetic equation. You would start taking moments of the kinetic equation, and this is what would give you your fluid equations. That's done in these notes later on. But you know, for the sake of being concise, I'm just going to write them down and we'll talk about them, and then we'll investigate some implications. So the first thing is just notation. If you use LaTeX, what I mean by this is var rho. And the reason I do this is because this is the Larmor radius, and I don't want to keep on using rho for two different things. But you know, just a warning, if you look through articles or textbooks, people use rho for both the mass density and the Larmor radius, and sometimes it could get confusing if it's the first time that you're seeing some things. Right. So this is mass density. So you sum up all the masses and number densities of all the species S in your plasma, and that's the mass density. So the first MHD equation is continuity, which is pretty self-explanatory. So this is the velocity. You might ask what velocity. We'll come back to that. What this says is that if you integrate this over volume, this is just a statement of mass conservation. So you have some fluid element. In MHD, fluid elements are technically infinitesimal, but it's just some collection of charges that obey some collective behavior that you can describe by some sort of macroscopic from the standpoint of particles. You can describe it by some sort of volume. Within that volume, the mass evolves, and you can use divergence theorem here. And so this is just the flux of mass through a surface of the volume. So if you have some volume, you have some mass in it. If there's a flow through the surface of the volume of density traveling at some velocity, that tells you how much that volume is leaking mass. So this is quite simple. If you have a multi-component plasma that you want to, instead of investigating some bulk properties like the total mass density, if you want to investigate the mass density of every single species, each one satisfies something like this.
Sorry, rho is E?
Rho is what?
E? Yes, you are mixing.
It's var rho. I haven't written any E's yet.
Rho. What's rho there? The second line.
Second line.
Third line. The last one.
No, yeah, sorry. So that's a trick. Var row is hard to write. Good, so that's continuity. If you go later in the notes, you can just derive this from the 0th moment of the kinetic equation. So that's continuity equation. Then we have a momentum equation, sometimes called a force equation, depending on who's writing it. You can just motivate this from Newton's second law. I'm just going to write it down and we'll talk about it. Well, I'll write it like this. Okay, so the left-hand side here, just going to write like that. So this is a time rate of change of the velocity of a fluid element. And what this term does is it makes sure that you're taking the time rate of change in the frame that's moving with the fluid element. So this is what I mean by this big d by dt. Sometimes this is called a co-moving derivative, which is quite descriptive. Or if you want to be fancy, it's also called a Lagrangian derivative for reasons that I'll come back to. Right, so this is just MA, right? The right-hand side are the forces. Here's an obvious force. This is just gravity acting on a fluid element, but you could replace any of your favorite velocity-independent forces with gravity. If there's any body force, if you're stirring the plasma, all that goes here. This is the gradient of the pressure. So if there are any pressure gradients in the system, this, it shouldn't be too surprising. I assume you all took basic physics. What is surprising here is that this thing is just a scalar. And that is a consequence of the collisional ordering that goes into MHD, which I'll talk about in a second. In the second lecture, we'll encounter a lot of systems where this is not a scalar. And this is what makes MHD MHD. So that's the Lorentz force. So J here, with apologies to Maxwell, was determined by Ampere. By writing this down, many of you know that implicitly I'm assuming non-relativistic motion. That's why I said with apologies to Maxwell, because there's no displacement current here. So of course you can write down a system of equations that are relativistic MHD, but I won't do that. So this is non-relativistic MHD. You have an Ampere's law that links the curl of the magnetic field to the currents in the system, which is just the sum of the motions of all the charges, and then cross B over C, because CGS. That thing keeps running away. Okay. While I erase, I'll tell you what Scott told me, which is that there's some sort of efficient way of using all these boards. I guess I've just demonstrated that I don't know that way. Okay, so some words about the Lorentz force. I understand that a lot of this would be basic to some of you, but it's worth going through. Um, So you look up some vector identities, and you write this down. And people usually talk about this as a tension, this is a pressure, but that's not actually quite right. And we'll come back to that. I understand that I keep on saying we'll come back to that, but we will. The point of writing this now is not to say we'll come back to that, but it's just to show you that there's this term here under a gradient, which you can stick along with the pressure. Right there. And so that's just to give you an indication that part of this Lorentz force just acts like an enhanced pressure on the plasma. All right, one last thing. So we need to know how the pressure evolves. And in ideal MHD, that's just determined by entropy conservation. So you just have a system. If it has no losses or gains, you know from your thermal physics course that the entropy ought to be conserved. And that can be written like this. So here's just d by dt. Remember, that's in the frame of the fluid. It's not just in the lab frame. So in a fluid element, as that fluid element moves within that volume, log p rho to the minus gamma, where gamma is some adiabatic index, degrees of freedom and all that, it's conserved. Now, there's nothing in MHD that necessitates the left or the right-hand side to be zero. Of course, you can add sources and sinks. In fact, most astrophysical systems have sources and sinks of entropy. If you want to do that, you just put a p on that side, and you change that 0 to a q. And this is just sources, sinks of entropy. I guess maybe a dot for good measure to remind us that it's a rate. So something I show just in a few lines in the notes is that in such a system where the sources and sinks are 0, if you have incompressible motions, so if the divergence of the flow is 0, this means that T is a constant. Actually, in a fluid element. So what I mean by that is the big D by dt. Good. So those are MHD equations, so I could just stop. So actually, they're extremely rich. There's a lot of assumptions that go into them which are worth talking about, because usually you can perfectly well use the MHD equations without actually knowing what you've assumed by using them. All right, so before doing that, just a quick word on this Lagrangian derivative, this d by dt. So this thing could be quite tricky. So later in the week, there will be lectures about accretion disks, which are often modeled using cylindrical polar coordinates. There'll be parts of lectures that are talking about Bondi flow or the solar wind, or certain accretion flows which are more close to spherical, or the sun, where you have to deal with spherical polar coordinates. And this thing gets really nasty in these different coordinate systems. And one reason why is that you have a gradient operator acting on a vector. So this, you have to worry about that. Right. And I've given you a few pages in the notes where I discuss that for a cylindrical system, and then I just write it down for a spherical system. And I'll just say a few words about that right now. So this is, I think one of the most difficult things in MHD is actually just getting the vector analysis right, because it's really easy to just drop terms. So the issue here is that you're taking, so this is for cylindrical coordinates. You're taking an azimuthal derivative of a vector, and inside that vector are these unit vectors. And I hope you recall that the derivative of these unit vectors is not 0. And what you get out of this, which I just do in the notes for you, it's just a simple exercise in vector analysis, is that you get something which ends up being a Coriolis force and something that ends up being your centrifugal force. And I'm not going to do vector analysis on the board. It's just here, so you can look it up. One thing that I do in these notes also, which I'll advertise, is if you're in a rotating system, so if your velocity is composed of some fluid velocity, just random motions, plus a large-scale rotation, if you're in an accretion disk, there will be talks about that. And if you sub this into this convective derivative, you'll get a whole bunch of extra terms, and they're all quite important. And I think it's a calculation that you should do if you haven't already done, is to go through being in a rotating frame and making sure that you can derive the appropriate momentum equation. So it's sketched in the notes. So. Good. Okay. So we've got a continuity equation, mass is conserved. We've got a momentum equation, F equals ma. We've got a energy equation, and the momentum equation has a magnetic field in it, and I've not said how to evolve that. Now, of course, any way that you evolve the magnetic field, it should satisfy that. So if you go to Maxwell's equations, there's Faraday's law, and yet another thing that I'll come back to is why in MHD is just that. You could also add, let's see, how do I want to do this? This is resistive diffusion. So the simplest way of arguing for this equation, which is called the induction equation, is by saying that in MHD, I have a near perfect conductor. So the electric field just satisfies some sort of Ohm's law, right? E is A to J. And then you have to be really careful about what you mean by your electric field. Is this the electric field in the lab frame? Is it in the fluid frame? What do you mean by the fluid frame? So this is the electric field in the fluid frame. And the way to convert between the lab frame and the fluid frame is just to add on a U cross B over C term. And now, you may be wondering, what exactly is this U? What species velocity is this? Is this some special velocity, or is this just the velocity of a fluid element? We'll come back to that when we talk about multi-fluid MHD. But in MHD, it's just the velocity. It's the only velocity in the problem. So that's where this comes from. It's just Ohm's law in the frame of the flow. And so I'm just going to give a few comments about what this implies. Everyone good? I understand a lot of you have seen this kind of stuff, but bear with me. Something I do on page 15 of the notes is I talk about the relative size of this resistive term in the Ohm's law to this term, which is sometimes called the effective term, which is not quite true, but the relative magnitudes of these terms are usually characterized by two numbers. One's the magnetic Reynolds number, one's the Lundquist number. I give these numbers in the notes. I'm not going to go through them because I'm not going to talk about things like reconnection where the Lundquist number is important. The only thing that you need to know is that in astrophysical systems, these are absolutely huge numbers. And I give some of the numbers here. So in the interstellar medium, the magnetic Reynolds number is 10 to the 18. So what that means is that on a lot of scales, this term is not important. Of course, you'll always get to some scale. There's a gradient here. There's two gradients here. So you always get to some scale where the gradients are so large that it doesn't matter how small eta is. Right? And that's when you start talking about reconnection and things like that, which I'm not going to talk about. This lecture, at least the first part of this, is about ideal MHD. Good. So there are two things that this equation implies. Because for now, I'll get rid of this. One is called the Lundquist theorem, and one's called Alfvén's theorem. So let's look at those. Now there's vectors and cross products and derivatives here, so it's a bit messy to look at it in this form. You can look up your vector identities and you can expand the right-hand side. And that's actually quite useful to do that, especially in curvilinear coordinates, because thinking about these gradient operators in curvilinear coordinates is a lot easier than thinking about these curls in curvilinear coordinates, at least for me. So there's three terms here. There would be a fourth, but there's no monopoles. And each of these terms has a straightforward physical interpretation, which I write in the notes. This is just stretching. I'll show you why in a sec. This is advection. And this is compression. So the idea is that there's some magnetic field that's being carried around by some velocity. That's what I mean by advection. I'll prove that it's carried around on one of these boards. Here, if there's a fluid flow with gradients, it results in stretching the magnetic field. That's what this term is. And this term is kind of obvious why it should be compression, because there's a velocity and there's a divergence. So either the fluid flow is diverging or it's converging. Either way, you're going to squeeze the magnetic field or rarefy the magnetic field. And that's what I'll prove to you now. So one thing that you can do is you can take this form of the induction equation and you can take that top form of the continuity equation and you can combine them. And that's done in the notes. The reason it's done in the notes is that I don't have to do it up here. And you get this equation. So remember this d by dt, it's the co-moving time derivative. So pick a fluid element, move with it, measure d by dt in that frame. And what I've done here is I've divided the magnetic field vector by the mass density, and it satisfies this nice equation. And that might not mean too much to you if you haven't seen it before, but what you can show is that if you have a point, some point x, which characterizes a fluid element, and that point is moving with some velocity u. And if I go a little distance away, squiggly letter, to x plus c, and then that other place there's another velocity, you can show just by some simple geometry. That. And so what this means is that this quantity, B over rho, satisfies the same equation as just a line being advected by some velocity. So what this means is that if you have a field line and it's in some fluid flow and the fluid flow is moving, that fluid flow is going to move along these trajectories, but so is the magnetic field. So this just says that field lines are fluid elements. If they start on a field line, they're not going to leave it. Field lines lie on, field lines that lie, fluid elements that lie on field lines initially remain on that field line. So this is called Lundquist's theorem. So it's the first little indication of something that's called flux freezing, that a fluid element carries around a magnetic field line with it. So there's two versions of flux freezing. This is one of them. This is kind of a weak version. There's a volumetric statement about flux freezing, which is Alfvé's theorem. And this is the one that usually gets presented first instead of this Lundquist theorem. So the idea here is that I have some surface. There's some magnetic field lines that thread. So here's some surface S. Here's the boundary of the surface, delta S. There's some surface element there. And I'm not going to do the derivation because it's just right here for you on page 17, that if you compute the flux at some time through some surface, so there's the surface. Now, if you move that surface according to the momentum equation, the continuity, if you move that surface such that every point in the surface obeys something like this, the flux doesn't change through that surface. So if you measure this flux and you take the time rate of change of this, as this surface evolves, this is going to be 0. And like I said, I'm not going to go through the steps because they're just done in the notes. There's no point in me writing this. But the salient point is just between Lundquist's theorem and Alfvé's theorem, what this means is that the magnetic field is frozen in the flow. So anywhere the fluid element moves, the magnetic field lines go with it. And so does the magnetic flux. Okay, any questions about those two? Because it's sort of fundamental MHD. Yeah? So that includes both. So if you have a ball of plasma that's sitting between or in a solenoid, and there's some external flux through the system, so that'll be conserved. And if there's any self-generated magnetic fields due to currents in the plasma, those will be conserved. Yeah. Okay. When am I done?
Aim for 10:30.
Okay, good. All right, so one of the things that I said I was going to come back to, I'm finally coming back to. And this is the Lorentz force. So we now know that the magnetic field is frozen in the plasma. So if the fluid moves, the magnetic field the field lines come with it. So now we want to know, what do those flux frozen field lines do to the fluid elements in which they're being infected, in which they're being carried. So I had showed you by virtue of vector calculus that the Lorentz force splits into two parts. One looks like a pressure, which goes in with the thermal pressure and the momentum equation. And then there's this other term with a bunch of vectors. You can rewrite this in a handy way. Yep.
Can I ask you a question?
Yeah.
How is the connection with the alpha theorem and the stream lines of the fluid? It seems that the stream lines of the fluid are the same.
It's exactly the same.
And how is compatible with if you have a divergent fluid, compressible fluid, for example?
Oh, it doesn't matter. So so you're referring to something called Kelvin's circulation theorem, which, if omega is the curl of U, this is called the vorticity, it satisfies an equation that looks identical to the ideal MHD induction equation. So you have the same sort of principles where the amount of vorticity in a fluid element as it's carried around by some flow is conserved. It's like a Kelvin circulation theorem. And Alfvén's theorem is just Kelvin's circulation theorem for the magnetic field. Doesn't matter if the flow is compressible or not. Yeah. Thanks. So by virtue of the magnetic field being divergence-free, you can write the Lorentz force in this full divergence form, which turns out to be quite useful. This thing's just called the Maxwell stress tensor. You probably saw it in E&M. So there's an isotropic part, that's the unit dyad, where the magnetic pressure lies, and then there's this tensorial piece to it, which has off-diagonal elements. And this is right here. This is what makes MHD MHD. Before this off-diagonal stress, the flow is fairly isotropic, right? This is the thing that introduces some sort of directionality into the system. It biases the system based on the magnetic field. Whether the field's strong and tells the fluid elements where to go, or if the field is weak and the fluid elements tell the magnetic field where to go, there's always this anisotropy introduced by the Lorentz force. So what I'm going to do now is I'm going to rewrite, this is something I haven't used yet. I'm going to rewrite this more physical form. Reason I don't like this is that people usually say the first term is pressure and the second term is tension, but that's not exactly true. So I'm going to introduce this unit vector. So if you have some field line, that's just a unit vector pointing in the direction of the local magnetic field. And what you can do is you can rewrite this Maxwell stress, well, the force, the Lorentz force, in the following way. So this is the Lorentz force, the magnetic force on the plasma. So what I've done is I've taken this big B dot grad B and turned it into a little B dot grad B, which ended up giving me an additional, this little B dot that, which is going to eat up part of the second term. The nice thing about this form is it's clear that this force operates perpendicular to the magnetic field, which is obvious when you write it J cross B, which is perpendicular, but it's not obvious in that form because that second term has a gradient, which has a component along B. So it's nice to write it in this form. Everything's perpendicular. This is just 1 over the radius of the curvature of the field lines. And this is a perpendicular gradient of the magnetic pressure, magnetic energy density. So I'll draw these pictorially. So this term over here, this is in fact the tension. So I have some magnetic field. Here's B at the surface. B dot grad B points in here, and it's sort of the radius of curvature of this field line. So another way you could describe this is just the curvature force. So a magnetic field that's bent wants to straighten out, and that's what this term says. So pictorially, what this is that if I have a bunch of magnetic fields that are pointing this way, and I compress them perpendicular to the direction. So that's what I've done here. So this is the perpendicular direction. Then there's a force. This is sometimes called a pressure force. So both of these things say that magnetic fields don't like to be messed with, right? They want to be straight, they want to be spread out. If the fluid, which is frozen into this field, curves the field, the field's going to want to back react on the fluid and straighten itself out. And it'll try to push the fluid in order to achieve this. The same thing here. If there's some compression in the flow, which squeezes the magnetic field in some direction perpendicular to its own direction, it's going to want to spread back out, which means it's going to exert a force on the plasma in order to enforce that, or in order to force that to happen. Right? So what this means is that, this is the fundamental difference between MHD and hydro. This endows the fluid with some elasticity, which it doesn't otherwise have. Okay, so that's ideal MHD. So what I want to do now is discuss some applications and then discuss some limitations. Does that say 10:15? Yeah. Okay. So one calculation that you all should do if you've never done before is linear theory. I encourage you to go through the notes tonight if you've never just done linear theory of MHD. I go through it in detail in the notes. Of course, I don't have time to do it at the board, but a lot of astrophysical fluid dynamics just rest on doing linear theory first. So what I mean by that is that you have some system characterized by some velocity, some mass density, some magnetic field, some pressure, and you construct some equilibrium, which at least in my notes, I just denote with the subscript 0. So there's some equilibrium. You'll hear from other talks later in the week about equilibria, how to set it up. Michael Barnes is going to talk about Grad-Strefanov equation, which is one way of determining equilibrium in like a tokamak, for example. I'm not going to talk about it, just suffice it to say there is some equilibrium, and what I'm going to do is I'm going to make little perturbations to this, which I was taught to denote by this delta. Now, it's quite important to note what I mean by this delta. This thing is called an Eulerian perturbation. There is something like this, which is called a Lagrangian perturbation. And just based on their namesakes, you should be able to tell the difference. So the Eulerian is a change in the quantity in the lab frame. So this is, and this is explained in the notes. So this is, for example, delta P would be P at some position minus the equilibrium P at that same position. Lagrangian P, the Lagrangian change, this big delta, just like the Lagrangian derivative, this big d by dt, it's a change taken with the fluid element. So this is P at some position which has been displaced from the initial position. So some fluid element moves, the properties inside that fluid element change, and that's what this Lagrangian derivative is, or this Lagrangian change is. So in everything that I'm going to do, I'm just going to use Eulerian perturbations because it's simple. It's important to do Lagrangian perturbations when you have things like you have some stratified plasma and there's some background fluid flow. And in that case, doing Eulerian perturbation theory is a bit tricky, and it's often easier to do it with these Lagrangian perturbations. I'll just do it with these Eulerians. So you have some equilibrium state, you perturb the plasma, and what I mean by linear theory is that every time you see a delta squared, you just drop it. So all the nonlinear terms are gone. And what I do here is a homogeneous, stationary plasma threaded by a uniform magnetic field. So that's what I do in these notes. So you take a stationary, this is a constant, this is a constant, this is a constant. You perturb the fluctuations. You can assume just take the normal modes of the system, and you just do linear algebra, and you crunch. And so all the derivations in the notes. I'm just going to talk about the results, and yeah, let's do this. And tell you some aspects of linear MHD. In 10 minutes. Okay, so one wave you get is called an Alfvén wave. You can have all sorts of Alfvén waves, but the one I've drawn has a wave vector which is only along the magnetic field. So this is called a shear Alfvén wave. It's polarized like that. This has no compressions in the magnetic field. It has no changes in the mass density. You know, it's quite boring. You just pluck the field like a string, and you find that the dispersion relation of the wave, the relationship between omega and k is just this, which is quite simple. So it's not dispersive. Omega over k is just a single number. It can propagate forwards or backwards. This is the fundamental building block of theories of turbulence. It's the fundamental wave. You can also, here, let me move this over. You can also just have a bunch of field lines that don't move, and you can put compressions here and rarefactions and compressions here and rarefactions, and then you just get a sound wave where this is the sound speed. So the idea here is that you've just made a bunch of compressions in the fluid, in the pressure, that launches a wave, and the magnetic field lines just don't care. So then there's a whole class of waves called magnetosonic waves, which are hybrids of these two. And like I said, the derivation's in the notes. I'm not going to do it here. But I will show you some examples. So if you have a wave vector which has both a component parallel to the magnetic field and a component perpendicular to the magnetic field. You can have field lines that end up being perturbed like this. Now, that's not enough to know what's going to happen to the wave. You also have to know how the pressure responds. And so there's two types of waves that come from this. So of course, right here, the magnetic field is strong because the field lines are bunched together. And right here, the magnetic field lines are weak because they're spread apart. And the two options that you get is whether you also have the gas pressure high here or the gas pressure low here. So if you have high pressure here, this is called a fast wave. I'll tell you why. If you have high pressure here, this is called a slow mode. And the difference is that here you've got two restoring forces acting in concert. Right? You've got some gas pressure that wants to expand the gas, and you've also got a magnetic field which is resisting being compressed. And so both of them try to spread out, and you launch this wave at a fast speed because you have both. You've got two pressures pushing on it. Here, the changes in the field strength and the gas pressure are anti-correlated. And you get into a situation where the combination of these two is quite small. So the two act in antiphase. So I go through gory detail in the notes about this. I've got 5 minutes, so I'm not going to say much more. But the dispersion relations are in the notes. The process of doing linear theory to derive these waves is in the notes. I encourage you tonight, if you've never done this before, it's really important that you learn how to do linear theory. Everything else follows from this. So the point of just the qualitative discussion that I've given here is that there are several different classes of waves. You have sound waves, you've got Alfvén waves, you've got these hybrids, which are called magnetosonic waves. There's basically two types of magnetosonic waves, a fast and a slow mode. There's also something called an entropy mode, which I think is attributed to Russell Kohlrausch, which just basically says that you just relabel all the fluid elements, and that's the entropy mode. So those are all the modes of MHD. So where I pick it up from there in the notes on page 25 is something called reduced MHD. I'm not going to go through this because I'm out of time, and I want to get to multi-fluid. But I've provided a lot of detail here. It's a technique, sort of more advanced MHD, that's used for describing Alfvén wave turbulence, which is, I think, something that Elliot Quatter is going to talk about. No, he's not going to talk about it, so it's good that I'm skipping it, because it doesn't matter. Anyhow, I think it's an extremely useful thing to know, particularly just from the mathematics. If you want to know how to do asymptotic expansions of equations, by which I mean you identify a small parameter and you do an asymptotic expansion of a set of equations in that small parameter, reduced MHD is sort of the entry point for doing that in MHD. I do it in the notes. It was first developed in the fusion community and then got into the solar wind community and the heliophysics community. I highly encourage you to go through these notes. If you know MHD already but you don't know how to do asymptotic expansions, it's worked out in the notes. For several pages. Okay, so I want to come back to the last thing that I deferred, which is probably on some board somewhere. No? Well, whatever. So one thing I deferred was when we wrote down the continuity equation, when we wrote down the momentum equation, when we wrote down the induction equation, I didn't actually tell you what the velocity was. I just said there is a fluid element velocity. Now, an MHD is technically defined as the sum over species of all the momenta divided by the total mass. So this is the center of mass velocity, right? So when you say U in the MHD equations, what you're really referring to is the center of mass velocity. Now, this can get really tricky for a number of reasons. One is that suppose the degree of ionization in your plasma was small. So suppose the number of ions versus the number of neutrals was small, which means that your fluid velocity is just your neutral velocity. You know, it makes no sense for a magnetic field to be frozen into a bunch of neutral particles. So you have to be very careful what you mean by U. You know, in ideal MHD, this is just a fluid element. But very quickly, as soon as you depart from ideal MHD, you have to be very careful about what this velocity actually means, particularly if there's a large component of the plasma that's just neutral. So you can ask a question, do the equations that I've been talking about still hold when you have not that many charge carriers? The answer is yes, with some corrections. You can ask the question, what changes? You know, we have this induction equation. You know, what is that velocity? I mean, it's surely not the neutral velocity. It just wouldn't make any sense. Why would a field line be tied into a bunch of non-charged species? So this is really important in molecular clouds and the interstellar medium and protostellar cores and protoplanetary disks. So that subject's called multifluid MHD, which I'll teach you all in 2 minutes. Is it?
It goes to 10:45. We're trying to allow some time for questions.
Oh, you guys don't have questions. Can I do multifluid MHD? Okay. Okay. So if you derive all of this from the Vlasov equation, you know, from the kinetic equation, which it's done in the notes later. I'll talk about this in the second lecture. What you'll find is that you have continuity equation for each species, denoted by an S. You have, I'll use the big D. Ran out of board. You have a force equation for each species S. So before I move on, let me say what I mean here is that there is some species with some mass and some density, which has an acceleration, which is measured. That time rate of change is measured in the frame of that fluid element. Each fluid has its own pressure, which in this case I've written it down as just a scalar, but it doesn't need to be a scalar, and I'll talk about in the second lecture. It experiences a Lorentz force, so the charged species have an electric field there's an electric field that they feel, there's a magnetic field that they interact with, and this is just friction. So technically this is the first moment of a collision operator, which is what I'll talk about later, but this is just friction between the different species. Now, if I were to sum this entire equation over all species, this term better vanish, or Newton's third law doesn't work. Right? So the momentum as an entire fluid is conserved with respect to collisions, but each individual fluid might exchange momentum by collisions. And of course, there's a thermal energy equation for each one of these. If it were ideal MHD, lossless ideal MHD, the entropy of each species would be conserved, but for sources and sinks. So, what is that? If I were to write down the induction equation for a multi-fluid MHD plasma, what do I choose for the velocity to stick into the induction equation? So the way I'll present it, you can actually derive a generalized Ohm's law, which I do in the notes, just very rigorously and step by step, but I'm just going to motivate this physically. So suppose there is some frame in which the flux is frozen, whatever it is. So I define U of the field to satisfy this equation. There's some frame where the magnetic field is frozen in. And what I'm going to do is I'm going to just add 0 a bunch of times. So suppose I had some electrons in the plasma. Suppose I had some ions in the plasma. Suppose I had some neutrals in the plasma. And I have to add that to make it all go away. So I've done nothing, right? I've just added 0 a bunch of times. Now, in ideal MHD, this is 0, this is 0, this is 0, and this is just the full fluid velocity, right? All the species move, from the standpoint of the macro scales, all the species move together. But if we had a system where the bulk of the plasma was neutral, and so the momentum, the inertia of the plasma was just dominated by the neutrals, it would really, really help to write an induction equation which looked like it was frozen in the neutrals, but for additional terms. And this is what it is. So we haven't really achieved anything. We've just added 0 a bunch of times. Now you've actually got to figure out how much does the ion velocity differ from the neutrals? How much does the ion velocity differ from the electrons? How much does the electron velocity differ from the field lines? And this brings in 3 topics. So ohmic dissipation, which is kind of related to that term. Something called ambipolar diffusion. Which is related to that term. And something called the Hall effect, which is that. I'm speaking quite roughly. If you had additional ion species, or if you had a bunch of grains like you do in protoplanetary disk, there would be additional species. I give you a reference in the notes where you can follow up on that if you're interested in more, adding even more species to a plasma. So this is just associated, it's just mocked up, basically, by an Ohm's law. So just the electric field due to this is A to J. So that's just straightforward resistivity, collisional resistivity. This, you know what UI over UE is, because you know that the current is the sum over all the charges and their velocities. And so this is just that if I only had ions and electrons. And if I have a neutral plasma, that means that these charges have to be the same. And so you know what the difference between the ions and electrons velocity is. It's just J. And we know that J is just curl of B. So a few words on this before I move on to ambipolar diffusion. The thing to notice here is that I have a difference between ions and electron velocities, and this is related to the curl of a field. All right, and I'm going to stick that in here. So I have curl of B cross B, so it's already nasty. And then I have curl of that. So there's two gradient operators, so it's kind of like diffusion. But it's anisotropic in the sense that, I've got all these cross products everywhere. So this introduces wave dispersion, which is something that you don't see in ideal MHD. Okay. All right, so we've got ohmic dissipation. It's just the disruption of currents due to collisional processes. We have the Hall effect, which is just the slippage of the ions past the electrons, which is related just to the currents that are in the plasma. And then we have ambipolar diffusion, which is the slippage between the neutrals and the ions in the plasma. So how do we determine that? Well, you have to ask, why would you expect these two to differ? Well, they don't in ideal MHD, and that's because everything is so collisional that all the fluids move in concert, right? So what that means is just turn down the collisions a bit. So I don't know how much to write on the board about this. I mean, it's all worked out in detail in page 37, 38 of the notes. I'll write down the answer and motivate it. So this is just force balance, basically. So I have a Lorentz force, which is acting on the bulk plasma, which contains mostly neutrals. And then I have a collisional drag. So if I can write it this way. So neutrals are colliding with ions. So you have a bunch of neutral particles around. They don't know about the magnetic field, but the ions do. So you collide with the neutrals, or you collide with the neutrals with the ions. Now the neutrals know about the magnetic field through collisions with the ions. This is the time scale of that collision. So this is like a drag force, right? It's a difference in velocities divided by a time scale. And this is Lorentz force. And this is worked out in the notes in detail, but the idea here is that you're balancing a Lorentz force that's acting on a charged species with a drag force where the charged species are talking to the neutral gas. And this is what allows you to have, that's what you plug in here. Now you notice that this is even more complicated than the other ones because it's J cross B, it goes right here, and then I cross it again with B, and then I take its curl. So there's two gradient operators, so it's like diffusion, but it's anisotropic because there's all these cross products with the magnetic field. So this is sort of the fundamental characteristic of non-ideal MHD in a poorly ionized plasma is that the diffusion is anisotropic. So I won't call it resistivity, I'll call it diffusion. So the magnetic field diffusion is anisotropic. And you can prove that for yourself. I give you the equations here. If you're looking for something to do tonight in your spare time, what I really highly encourage you to do is if you've done linear theory of waves before, you know the Alfvén wave, you know the magnetosonic modes, what you should do is take the generalized Ohm's law that's derived in the notes and what I've just talked about, which gives you a generalized induction equation, and use that to redo linear theory for these waves. So what happens to the Alfvén wave when there's some drift between the ions and the neutrals? What happens to the Alfvén wave when there's some drift between the ions and the electrons? What happens to the slow mode? What happens to the fast mode when each of these happens? It's a very straightforward calculation. It's sketched out in the notes, and it's something that I really encourage you to do. Once again, if you're really interested in astrophysical fluid dynamics, which I guess you're here, so yeah. If you want to learn how to do nonlinear problems, the first stepping stone is linear theory. If you could do linear theory and really understand the physics that each one of these introduces and how it affects all the waves of MHD, that's a really, really good first step. So I'll just give you a tiny bit of foreshadowing, and then I guess we'll have questions. So going all the way back to the first, the big chart that I erased, and then this chart, which I miraculously left up, So you can ask, we just learned MHD. We got a little taste of non-ideal MHD. I mentioned something called reduced MHD, which I didn't talk about, but it's derived in the notes and talked about in detail. Where can I actually use any of these things? In the solar wind, people have used reduced MHD for a long time to look at the turbulence. It's technically valid at large scales, but pretty much nowhere else, so it doesn't really work. MHD doesn't really quite hold in the solar wind because the solar wind's fairly collisionless. And we also observe the distribution functions not to be Maxwellian, so MHD doesn't really hold. Ideal MHD doesn't hold. The intracluster medium is extremely hot. It's fully ionized, so that's really good for MHD. But if you look down here, the mean free path can get kind of long. So the collisions aren't quite strong enough, so MHD is marginal. It turns out that you can modify MHD to look at a lot of the things in the intracluster medium. That's something I'll talk about in the second lecture. So that doesn't really work there. So if you go to galactic center, you see the mean free path is roughly the size of the Bondi radius. So that's not good if you're interested in accretion. You can't really use MHD that well. Particularly if you keep on marching in, if you keep on going into the galactic center, you get within 100 short shield radii of the central black hole. The mean free path is huge. So it's not really a fluid, so that's great. We just wasted an hour and a half. Interstellar medium is really, really good for MHD. If you look at the mean free path is tiny. It's not so tiny compared to the Larmor scale, so that means it's magnetized. Of course, the interstellar medium is a very diverse space. There's a warm phase, which are the numbers I've given here, but there's also a cold phase. In the cold phase, things are poorly ionized, and so you have to worry about this kind of mess that I've talked about, multi-fluid MHD. But it's still all within the context of MHD. You can add additional species. There's dust grains and things like that. And you can incorporate them all within the MHD framework quite cleanly. So that's useful. So 1 out of 4 ain't bad. Okay, I think I'll stop there. Thanks.